All right, more programming. So last video I had left off with this on this question, and I was a little confused about normal order and applicative order. I rewatched a video that I'd seen before, which I'll try and remember to put in the description. Functional languages evaluation order, and particularly this slide in the video was helpful. So I came back to this and I realized, so basically, and by the way, if you run this in bracket, it doesn't like it just keeps looping. It doesn't like terminate. So basically, and I didn't realize this right away, but so this is like a recursive without a base case, basically. So if this runs, it's just gonna loop forever. So I think the point of this is because applicative order is eager, then if an interpreter is using applicative order, then what's going to happen is, when you run this, it's going to substitute, like it's going to evaluate what y is, which for y, we've passed in this p function. And so it's going to try to evaluate that. And then it's going to say, okay, well, we have, p tries to evaluate p. It's going to get another call to p, and on, and so it'll never stop. Whereas if if the interpreter was using normal order, then it would say, okay, so first let's like it wouldn't evaluate anything, or it would go step by step. It'd be like, okay, so if, and then this part, and it'd say, okay, now I need to see if x is 0, and if it is equal to 0, then, and it would be in this case, then the program would return 0, test would return 0, and then we'd be done. And this recursion would never get rolling, and so you wouldn't have a problem. And because bracket uses applicative order, then if you run this with this, if you define these and then you call test with these values, then you get an infinite recursion, and that's what happened, and I needed to stop it. So, all right. So let's see. 1.17 example square roots by Newton's method. Oh wait, there was one that I'd skipped because it was unreadable. Translate the following expression into prefix form. I could just make up some numbers to fill in but I'm just not that into this. Looks kind of boring, so I'm just gonna skip it. Okay. Example, square roots by Newton's method. Okay. Procedures as introduced above are much like ordinary mathematical functions. They specify a value that is determined by one or more parameters, but there's an important difference between mathematical functions and computer procedures. Procedures must be effective. So I guess I'm going to say what they mean by effective. As a case in point, consider the problem of computing square roots. We can define the square root function as square root of x equals the y such that y greater than or equal to 0, and y squared equals x, right? Meaning, right? So the y such that both these things are true. That is within my limited mathematical comfort zone. So I'm gonna trust my ability to follow this example. This describes a perfectly legitimate mathematical function. We could use it to recognize whether one number is the square root of another, or to derive facts about square roots in general. On the other hand, the definition does not describe a procedure. Instead, it tells us almost nothing about how to actually find the square root of a given number. Right, like having a definition that gives you useful information is very different than having like a worked out way of finding things that meet that definition. So they say, it will not help matters to rephrase this definition in pseudo-Lisp. Didn't they do that? Define square root x, the y and greater than or equal to y equals 0 equals square y. Yeah, that doesn't help. The contrast between function and procedure is a reflection of the general distinction between describing properties of things and describing how to do things, or as it is sometimes referred to, the distinction between declarative knowledge and imperative knowledge. In mathematics, we are usually concerned with declarative what is descriptions, whereas in computer science, we are usually concerned with imperative how to descriptions. I'll skip this for now. How does one compute square roots? The most common way is to use Newton's method of successive approximations, which says that whenever we have a guess y for the value of the square root of number x, we can perform a simple manipulation to get a better guess, one closer to the actual square root, by averaging y with x over y. The square root algorithm itself was developed by Heron of Alexandria. Suppose our initial guess is 1. Oh, I managed to skip over. For example, we can compute the square root of 2 as follows. Suppose our initial guess is 1. So, right, so this is the number whose square root you're trying to find. This is your current guess. This is the quotient of those. And this is the current guess. And then you average those. You get a new guess. And then you repeat, basically. So they say, now let's formalize the process in terms of procedures. We start with a value for the radicand, the number square root we are trying to compute, and a value for the guess. If the guess is good enough for our purposes, we are done. If not, we must repeat the process with an improved guess. We write this basic strategy as a procedure. Define square root iteration, I guess. Guess x. If good enough, guess x. Right, so if, then we're basically running this thing that's going to determine if the guess is good enough. Then, right, so I just need to reread this. So, right, we have two values. Got the guess and the number whose square root we're trying to compute. And so we're going to have something which determines if the guess is good enough, a guess for the the number that the square root we're trying to figure out. And if it is, then the guess gets returned and we're done. And if it's not, then we're going to iterate. This is a recursive call. And actually, no, this is, I misspoke. What we're doing, we're calling something else, which is going to improve the guess. Right. I see what I totally misanalyzed this. Okay. So, well, actually, it is recursive. Yeah, because it's calling the same function, same procedure, but it's also doing something where it's calling something to improve the guess, and it's going to pass the improved guess to the recursive call and also the value of the square root, because that remains constant. Because we're always, whatever our guess is, we're always looking for the square root of the same number. So okay, I think I've got a handle on it now. The guess is improved by averaging it with the quotient of the radicand and the old guess. Right, so that's the improve thing. All right. So what do they mean by good enough? The idea is to improve the answer until it is close enough so that the square differs from the radicand by less than a predetermined tolerance. Yeah, I mean, that makes sense. I thought it would be something along those lines. Right. So the difference between the guess, between the square of the guess, because that's and the radicand, the absolute value of the difference, I should say. And they're doing absolute value because then it doesn't matter if it's if the guess is a little above or a little below. Like if your guess, when you square it, the resulting number is a bit above the actual number whose square you're trying to find, or a bit below, then as long as it's within the tolerance, it doesn't matter. It'll still register as good enough, which is the behavior that they want. That makes sense. So right, the absolute value of the difference between the square of the guess and the radicand is less than 0.001. And if that's the case, then it's good enough. And then they say, finally, we need a way to get started. Actually, I skipped over the averaging stuff, so let me read this more carefully. A guess is improved by averaging of the quotient of the radicand and the old guess. So average just takes the sum of an x and a y and divides those by 2 and divides that sum by 2. And then to improve the guess, we average the guess and the quotient of the radicand and the guess. Okay. So then I say, finally, we need a way to get started. For instance, we can always guess that the square root of any number is 1. Define square root x. Oh, I see. So if you define this, then this will pass in 1 as the guess, and then whatever number you're trying to find as that number. So you don't have to type in a separate guess. And I guess that's fine because like even if you're trying to find the square root of a big number, like the computer's going to do the calculations pretty quick. So you don't need to worry so much about the starting guess. So let's try that. All right, so all the results were as expected, except for this little typo where I forgot to put a space here. So the square root program also illustrates that the simple procedural language we have introduced so far is insufficient for writing any purely, or is sufficient for writing any purely numerical program that one could write in, say, C or Pascal. This might seem surprising since we have not included in our language any iterative looping constructs that direct the computer to do something over and over again. Square root iter, on the other hand, demonstrates how iteration can be accomplished by using no special construct other than the ordinary ability to call a procedure. So there's an exercise. A SICP hacker doesn't see why if needs to be provided as a special form. Why can't I just define it as an ordinary procedure in terms of cond, she asks. Alyssa's friend Eva Luader claims this can indeed be done, and she defines a new version of if. All right, so I tried to do this exercise and I got a little stuck. And I looked at, because you can see what a program is doing if you use trace. And I at least figured out where the problem is. I haven't necessarily figured out what the problem is, but at least where. So if you define square root iter in this way with this new if, and then you pass a number to it, it seems to start out okay. You pass in the default guess and the number. It tests if it's good enough. You get false because, you're way off. And so it goes to improves the guess, tests if it's good enough, false. Okay, you keep going down. And then eventually, and so here's where the problem starts. You're getting a square root number that's, estimate that's pretty close. You pass that in. The number meets our threshold for being good enough that we set where it's, within 0.001. But then improve is getting called again. Now, if I'm reading this correctly, at least the intended behavior is, so for new if, right, which is in the square root here, square root iter, is, we call this, and if it's not good enough, okay, if it is good enough, then we just return the guess and we're done. So, so based on that, at this point, we should return this value in the program, or at least that was the intended behavior. But if it's not good enough, which was the case up until we got this number, then it will call square root iteratively with a call to improve guess as the first, the first parameter or whatever. So, but what it shouldn't be doing is getting something that's good enough and then continuing to call square root iteratively or recursively. Now, why is this happening? So, if is a special form, like the regular if, and it says here, right? So, special form if, a restricted type of conditional that can be used when there are precisely two cases in the case analysis. The general form, yada yada. To evaluate an if expression, the interpreter starts by evaluating the predicate part of the expression. So, the predicate is the thing that's going to give you the true or false value. So, in the standard if way of defining square root iter, the predicate was this. And in our newfangled way, well, right, we're using cond instead of if, but it would be this for our new if. I mean, we're using cond in the background, but okay. So if the predicate evaluates to a true value, the interpreter then evaluates the consequent and returns its value. So this was the consequent with our original way of defining if. And this is the consequent in our new if. Otherwise, it returns it evaluates the alternative and returns its value. So let's look at cond then. Conditional form, general form of conditional expression is this, consisting of the symbol cond followed by parenthesized pairs of expressions PE called clauses. The first expression in each pair is a predicate, that is, an expression whose value is interpreted as either true or false. Conditional expressions are evaluated as follows. The predicate, P1, is evaluated first. So, in the way we've set this up with this new if using cond, this would be based on how we're, the whole thing would be the predicate. And this was the first evaluation. So it got evaluated. It produced a value. If the value is false, and we have false, then P2 is evaluated. And, oh, wait, no. Let's back up. So if its value is false, then P2 is evaluated. P2's value is also false, then P3 is evaluated. This process continues until a predicate is found whose value is true, in which case the interpreter returns the value of the corresponding consequent expression of the clause as the value of the conditional expression. So that sounds to me like that should be, this evaluation method should be compatible with, like, when we, even though we're calling this recursively, at some iteration of square root iteration, when we get to when it evaluates as true, that should be the base case, And then the interpreter should return the value of the corresponding consequent expression of the clause as the value of the conditional expression, meaning in this case that when this evaluates as true, then it should return this value as the guess, and we should be done. But that's not happening. If none of the p's is found to be true, the value of the cond is undefined. Wonder if that is significant. All right, let's read this. Else is a special symbol that can be used in place of the p in the final clause of cond. This causes the cond to return as its value the value of the corresponding e whenever all previous cases have been bypassed. In fact, any expression that always evaluates to a true value could be used as the p here. So I think I know how this program is supposed to function. I think I know how normal if and cond function. I think I know roughly where the problem is in terms of, or like, well, I mean, I roughly know what's happening with this program in terms of like, it's not doing what it's supposed to, and it's not, like the new if isn't evaluating the true value and then stopping when it's supposed to. It just keeps going. But I'm not sure why that's happening. So I'm gonna stop the video here and maybe put the fact that I got stuck in the video description and ask FI for help.